All right, we're going to do 2110 and 2111 on this one recording. 2110 being the propagation of electromagnetic waves, and 2111 being the properties of electromagnetic waves. So let's go to the PowerPoint. And from our studies of electricity, whenever you have positive charges, you have an electric field radiating from them. So if we look at this dipole antenna, it's easy to understand that you have an electric field going away from the positive charges and towards the negative charges. And after a period of time, the electric field is diminishing and it's neutral at t equals t to the fourth, and then it reverses directions. And now so at first they were going away from the positive downward. Now they're going away from the positive upward. And you can see as this repeats, you get this sinusoidal E field that's propagating away from the dipole antenna. Let me catch up on my notes here. See that. Okay, so whenever a charge accelerates, whenever a charged particle accelerates, it radiates energy. So it's radiating energy down down away from the antenna. Also, whenever you have a current in a wire, you're producing a magnetic field. So the fact that we have a changing E field and a changing B field, we get both the electric and magnetic fields are sinusoidal and perpendicular to each other. Both fields are perpendicular to the direction of wave propagation. And I've got my friend Walter Fent waiting in the wings so that you can see the propagation. You can imagine in the Y, along the Y-axis, a dipole antenna that is producing the red is the electric field. The blue is the magnetic field. Now there's another right-hand rule that we can learn. Also this is a transverse wave. You remember a longitudinal wave, we had the little slinky longitudinal wave is a compression and rarefaction of the waves along the direction of propagation. This a transverse wave. When I took the slinky and I just shook it, that's a transverse wave. This is a transverse wave. Both the E and the E field and the B field are transverse waves, and they're orthogonal to one another. So there's another right-hand rule. If you take any of these upgoing E fields, the red, if you take them and you curl your hand into the magnetic field, your thumb is in the direction of propagation. So that's another right-hand rule. Point the fingers of your right hand in the direction of E, curl them in the direction of B, and the right thumb then points in the direction of the propagation of the waves. Yet another right-hand rule. And so that's, I thought I had a little app that showed a dipole, propagation of a dipole antenna, but this does it well enough. Now we're going to move on to properties of electromagnetic waves. And Maxwell found this relationship also. The mu sub zero, we've studied both mu sub zero and E sub zero. The mu sub zero being the permeability of a vacuum, and E sub zero is the permittivity of free space. Well, the speed of light is equal to 1 over the square root of mu sub 0, E sub 0, where mu sub 0 is 4 pi times 10 to the minus 7 Newton second squared per Coulomb squared, and the permittivity is 8.85419 times 10 to the minus 12 Coulomb squared over Newton meter squared. And if you calculate all of that out, you're going to end up with meters per, you end up with, in the denominator, second squared over meter squared. If you take the square root of that, and since it's in the denominator, you'll reverse it, you'll get meters per second. And I've got, let's see if I have, yes, I don't know if you'll be able to see this, but I put it into my little Mathematica and called the speed of light. 1 times the square root of both of these, and you get 2.99792 times 10 to the 8th. And back to the PowerPoint, C is equal to 2.99792 times 10 to the 8 meters per second. Well, for all practical purposes, we use 3.0 times 10 to the 8 meters per second, and that's good enough to get the speed of light. I mean, for all calculations, for wavelengths and stuff, that the 3.0 times 10 to the 8 meters per second will work. Now, Maxwell also proved the ratio of the magnitude of the electric field, E, to the magnitude of the magnetic field equals the speed of light. So E divided by B equals C. Okay, let's go on to more properties of electromagnetic waves. Now we have I here that looks like current, but it's not current. It's intensity, the intensity I. The intensity I is equal to E max times B max divided by 2 over mu sub 0. And EB, from the last slide, we have E divided by B equals C. And so E max is equal to CB max, which is equal to B max divided by mu 0, the square root of mu 0, epsilon 0. Okay, let's look at more property. Where did I miss that? The intensity equals E max squared 2 mu 0 C equals C over 2 mu 0 B squared max. I'm not going to hold, these are just interesting properties. I'm not going to really test you on this. It's just information. Now, when an E&M wave, we're going to learn that they have, E&M waves also have momentum. Mu is equal to the intensity times the area of an object times delta T. So when an E&M wave strikes an area A of an object's surface for a given time of delta T, energy is transferred to the surface according to the relationship shown. Momentum is also transferred, and that means that when an E&M wave hits a surface, pressure is exerted on it. Now, if the momentum is equal to mu over C, you get complete absorption. Now, do you remember when well, I didn't have y'all last semester, but if we talked about momentum, if you talked about a ball ricocheting off the wall, you would have M times V. It was a change in momentum. M final, momentum final minus momentum initial, uh, if it were, that's the delta, that's a change in momentum. If it were bouncing off a wall, you had a V, and then if it bounced off the wall with roughly the same velocity, you had a minus V. So you had m times V minus a minus V. You ended up with 2 mV. So you had double the change in momentum. So if you have complete reflection of the electromagnetic wave, the momentum is now 2u over c. So it's complete reflection. You get that same doubling of the velocity. So there we go. And here's a little device for measuring. The black disk will completely absorb, and the light reflected will the light will be reflected on the mirror surface, and so the radiation pressure can be determined by measuring the angle at which the equilibrium occurs. So in other words, this little fiber will cause this thing to rotate, because there's double the momentum off the mirrored section, and the other is being completely absorbed, so it has less momentum. And you can measure the radiation pressure by measuring the angle at which this thing turns. Other experiments also show that E&M waves, electromagnetic waves, they carry angular momentum as well. So these are this is the summary of the properties of electromagnetic waves, and this would be, some of these would be good quiz questions. So pay attention to these. E&M waves travel at c, the speed of light, 3.0 times 10 to the 8 meters per second. E&M waves are transverse waves. They're not longitudinal waves. They're transverse waves. E over B is equal to C, and the electromagnetic waves carry both energy and momentum. Okay, the ratio of the number 3 is the ratio of the electric field to the magnetic field in an E&M wave equals the speed of light. Okay, so those 4 properties, any one of them would be eligible for a quiz question. All right, and I think that ends our discussion. Next, we're going to discuss the spectrum of electromagnetic waves.